Thank you very much. Thank you very much, Dean. Ladies and gentlemen, welcome, my own welcome to you tonight. I'm going to talk about coping with a big nuclear accident. I actually mentioned this to a friend of mine who then discussed the matter with her 17-year-old son, who said, short talk then. Everyone's dead. Well, I'm afraid I'm going to disappoint you in both particulars of that statement. So I'm going to talk about coping with a big nuclear accident, and I'm going to start with fundamentals because I think we all should be at the same level on this. First of all, it's physically impossible for a commercial nuclear reactor to explode like an atom bomb, which is what my friend's grandson perhaps was thinking about. But the problem with nuclear reactors is even when you shut them down, you can't stop the heat production immediately. So you need continued cooling. And if you don't do that, the decay heat will build up and it will melt the core, and the core will melt through whatever containment structure you have there, and then it will then disperse radionuclides, radioactive fallout, which can then be taken up and deposited around the surrounding area. What you're concerned about is minimizing the radiation exposure of the public who are living near the plant. And again, looking now at the harm from nuclear radiation, on the right-hand side of that graph in red, the red bars there, this is where we get radiation cancers over around about 500 millisieverts. A sievert is an energy term, it's a joule per kilogram, and a millisievert is the standard term which is used of that energy deposition. And if that's above about 500, then you can have radiation sickness. That is to say, you can vomit, lose your hair, and in extreme cases, at the top end, die. And the LD there is lethal dose 50. 50% of people will die when they get something in the order of 4,500 to 5,000 millisieverts dose in a short time. And the lethal dose is somewhere 9,000, 10,000 millisieverts. You will be killed and die within a short time, hours. But the doses to the public do not lie in that area at all under basically any conditions. And I've put in a sort of a slightly fuzzy area there in blue, which indicates the possible public doses. What you're concerned about with these doses is you're concerned about developing fatal cancers, or cancers of any kind, some of which will be fatal. And the probability of developing those goes up as developing a fatal cancer goes up as the dose goes up. Meanwhile, down at the bottom in green is the natural background radiation, which you'll accumulate over a year, and it's around about 2 millisieverts, and that applies roughly to many places in the world, and it applies to the UK. Now, the Chernobyl accident is the worst accident we've ever experienced, and there the reactor went super prompt critical, which went the closest it could go to being a bomb. It was not a bomb because the energy that it released, it didn't release this over the microseconds needed for an explosive. It released this over a period of a few seconds before shutting itself down. And that's the Nordheim-Fuchs phenomenon that hot uranium is not such a good reactor, and the system shuts down immediately. But before that, of course, it had melted fuel, and that fuel had come out of the reactor. There had been an explosion caused possibly a steam explosion, and more likely a hydrogen explosion caused by a chemical reaction. And the devastation was very, very significant. And of course, we had a huge power excursion. 30 people died in the immediate aftermath, 28 more or less immediately, and another 2 from acute radiation poisoning, and they died within 3 to 6 months of the event, the poor unfortunate people there. Mostly from acute radiation exposure. There were some blast effects, there was some burning effects, I believe, but mostly from acute radiation exposure. Now we come to the principal policy response after Chernobyl, which was mass relocation of the public. We want to keep the public safe, let's move them away from the source of danger, was the thinking. And so a huge number of people were relocated. 116,000 in the days and months after the accident, which happened in April 1986. And then a further 220,000 were relocated after 1990. So the total was 335,000, and as you can see, that corresponds roughly to a city the size of Cardiff. Bristol is a bit bigger, but it would be an awful lot of Bristol would fall into that category and be moved. The Fukushima Daiichi nuclear accident, this happened 25 years later, almost exactly 25 years later, in March 2011. It was a great earthquake, the Tohoku earthquake, 80 miles offshore, magnitude 9, huge earthquake. 18,500 people were killed by the tsunami that followed from that, and it caused the reactors to undergo very significant harm. What happened was that they shut down automatically, as they should, having detected the earthquake, but that's not good enough, because if you remember the decay heat that I mentioned before, that decay heat needed to be taken away, and the problem was the tsunami inundated the pumps that were taking that decay heat away after about 45 minutes. They lost function, and so we actually had 3 reactors melting down, and a 4th reactor was actually, the fuel pond was damaged, and in fact there were 4 explosions there. A very significant release of radioactivity and hence nuclear fallout. But you'll see a pattern emerging now, and that is that the principal policy response after Fukushima was mass relocation. So over 110,000 people were asked to leave within a few days, and another nearly 50,000 saw what was going on, and they decided to leave anyway of their own accord. Problem with this is 85,000 people had not returned to their homes after 5 years, and probably not many more have returned in the intervening 2 years since the research, that paper was completed. Moreover, there were a number of people who died of this. These were principally elderly people who died, and they died early as a result of physical and mental exhaustion. Now, the Prime Minister of Japan at the time, Naoto Kan, was considering evacuating Tokyo, which was 150 miles away. This would have been an enormous decision to take, and you can see his comments there. It would have been like losing a huge war. Those comments were made 5 years afterwards, and that was that's what he's telling of what actually happened at the time. I think the thing to bear in mind there was the panic and disarray, which his words quoted in the Daily Telegraph, which the government was in at that stage. Excuse me. So that was the background against which the NREFS project was conceived. Big nuclear accidents, yes, they're very rare things, but we now have had 2 very big nuclear accidents. And we've had a few significant accidents, a few accidents that have spread significant amounts of radioactive fallout. The radioactive waste tank explosion in the USSR in 1957. Here in Britain, the Windscale pile fire in the UK, where a reactor, one of the first generation, very simple reactor, which was there to produce plutonium for nuclear weapons, that underwent a fire because the Wigner energy had not been released. Essentially, the metallic fuel had not been annealed, and it came out in a rush. And then a fire occurred. There was a widespread release of radioactive material into the atmosphere. So the question that we were looking at was, how should we cope after a big nuclear accident has actually happened? One of the worst, these are as bad as it gets as far as nuclear is concerned. Is mass relocation and abandoning of homes, is that the best strategy? It's been used in now 2 big nuclear accidents that have happened in the world. And then more generally, the research question was, how should we respond after a big nuclear accident has actually occurred? The NREFS project, which the Dean has described there, 4 universities and continued here at Bristol. I think it may not perhaps be a surprise that once one has actually finished doing the actual research, translating that into the final set of research papers is never a trivial, nor often a very short task, but that has now been completed, and we have publication of those papers, of 10 papers, which are there in Process Safety and Environmental Protection, a special issue of that journal. The feature of the NREFS project was it decided to attempt to apply mathematical tools, and it was clear from what had gone before that what was needed was something to help alleviate the fog and confusion that naturally occurs after a big nuclear accident. Another feature was that we actually used in the NRF study, we used 3 independent mathematical methods. The J value, J for judgment, and I will say a bit more about that in a moment. I will describe each one to a certain extent. The J value assessment, and we applied that to Chernobyl, these 2 big nuclear accidents, to Chernobyl and Fukushima on a retrospective basis, that if we knew now what we knew, if we knew then what we know now, what would we do? Would we still do those things that were actually done? And then optimal economic control, which actually included health effects, were applied to hundreds of conceivable nuclear accidents all over the world. That was work that was led by Manchester University. And then we applied the codes that had been developed by Public Health England for looking at consequences of nuclear accidents and the costs associated with those consequences. And we applied that to a big nuclear accident assumed to occur on a UK reactor located in a fictional site halfway between Southampton and London. And that was led by the Open University. So what are the policy options? First of all, temporary evacuation, but this is really something which is quite short term, where you might move people out on a precautionary basis, but you would get them back within days, or at least certainly a week or 2. Then, moving on, relocation, which is what's happened before, and people have been asked to abandon their homes either forever or at least for a very long time, with all the consequences that that brings about. If you can imagine you've been away from home for 5 years, how much do you really want to move back to that? So relocation, food bans, temporary or long-lasting, or even in the limit permanent, and then remediation. So this is cleaning up, urban decontamination, agricultural decontamination. To talk about the first method, the judgment or J value, what we're looking to do there is balance the life expectancy that a safety measure brings with it against the cost of providing that safety measure. And it's that balance that enables us to say that if the J value, we take J as being the ratio of what you are spending or what you're considering spending divided by the maximum that you ought to be spending, and that tells you that if J is greater than 1, you're spending too much. And the unique feature of this is that it is entirely objective. There is no opinion involved in it. It's based on data from millions of people, both actuarial data, life statistics, life tables, and also on millions of people and economics. So it's economic and actuarial data, and it is completely objective. That is to say that any team around the world could use that same method and they would come up with the same answers. One of the things that we did during the development of this was to actually validate the J value against pan-national data. And what we were able to do was to explain the Preston Curve. Preston Curve, Samuel Preston, in 1975 pointed out that GDP per head has a huge influence on how long people live at birth. And that's the graph for 180 countries in the UN, 193 in the UN, and that graphs the life expectancy at birth. And we were able to explain that, and we were able to explain 80% of the variation between countries, which is a pretty high figure for any social science study, which this effectively is in this instance. Well, we did that for 162 out of 193, and 60% if we actually looked at the full set of on which we had data, 180. And what we found was that the J value emerges as a formalization. It's what people do, basically. It describes how people take their decisions on safety in all countries, in all areas of the world, taking into account the resources they have available. That is to say that if we were in any other country in the world, we would act pretty much as those people act, and we would take the decisions that those people take. I'm going to mention some figures on life expectancy because I'm going to talk quite a lot about life expectancy, so it's a good idea to put something concrete down. The life expectancy at birth in the UK is around about 81 years. Excuse me. 42 years is the population average. So if we actually take how long is everyone going to last from now? If we looked at the whole nation, we'd say, well, people are going to live on average 42 years before they die. It's average across all ages. Now let's come down to some particulars here, and this one was something which always upset my colleagues at Manchester. It just happened to be so. I happened to be working in London. They were working in Manchester. 3.25 years lost by someone who moves from North London, in Harrow in North London, to Manchester. That's the average person. And it's 6.5 years if you do it at birth. And then 4.5 months is what the Londoner, by contrast, loses to London's air pollution. And that's on average across the population. It's 9 months at birth. Now let's look at some, to put things in context, let's look at some losses of life expectancy after the Chernobyl reactor accident. Well, we in this country, looking at the standard way of calculating the harm caused by radiation, we lost just under 3 hours of life expectancy in this country because we had some fallout in this country. The 116,000 people who moved away, how much life expectancy did they lose? Less than 10 days. But that's not the question. The question is, what would have happened to them if they had actually stayed in position? Those 116,000 making up the first relocation. Well, 85,000 of those people would have lost, on average, just 3 months life expectancy. So if the world's worst nuclear reactor, 85,000 of the people in that first evacuation would have only lost 3 months life expectancy. That's only 2/3 of the figure that people in London are losing as I speak. 31,000 would have lost more than 9 months life expectancy, and according to our method, the J value, we would say they ought to move out. It is worth it for them. And if we actually stipulated that whole villages or towns, settlements, needed to be relocated, if 5% of those people needed to be relocated, that is to say their loss of life expectancy was 9 months or more, then the figure would rise to 72,000. But that's still quite a lot less than 116,000. Now let's move on to the second mass relocation after Chernobyl. Now 220,000 people were relocated. This is 4 years later. Why did they do this? Well, 220,000 people were relocated after 1990. If we look at the most highly exposed 1,000 of those, they would have lost less than 3 months life expectancy. So, not surprisingly, the J value recommends that you shouldn't have moved any of those people. So in total, 80% of the people who moved after Chernobyl accident should not have been, according to the J value. That's a city the size of Derby should not have been moved. Now let's have a look at Fukushima Daiichi. Well, Fukushima Daiichi was by no means as serious an accident as the calamitous accident that happened at Chernobyl. The worst affected people there were inhabitants of a small town called Tomioka, and they faced the highest radiation dose in year 1. But it was only 51 millisieverts over the whole of that year. And that will have fallen to the safe return dose, which is what the Japanese government has stipulated, 20 millisieverts per year after about 6 years. That's about now. Some of the villages started off with less dose than the 20 millisieverts per year safe dose. One of those is Naharaha town, but you see there that people moved out and very few have moved back. So what was the benefit of moving out? For people in Tomioka, who were the most exposed, then they would have gained somewhat less than 3 months life expectancy by relocating for 6 years. And if they then, and having come back, they would then lose a further 2 or 3 months from the living under the safe relocation dose. One of the things about this is that that the dose is falling away at all times, and that's what the graph on the inset graph on that shows you. That if you get, it's 51 millisieverts in year 1, but it's falling away very rapidly and is a lot lower by year 5 and year 10 and so on. So was it worth it? No. As far as the J value is concerned, it's difficult to justify relocating any of those 160,000 people who are relocated after Fukushima, the accident at Fukushima Daiichi. That's what the J value recommends, and to put it in context for intuitive purposes, we're talking about less than 2/3 of the air pollution toll on Londoners. And if you think that J value is actually encouraging people to take risks, I can tell you that it values life much higher, much higher than the UK government's value of a prevented fatality, which is the standard method for cost-benefit analyses in the UK. That has its own problems which have been pointed out, and it is, but in addition to that, even if we put those problems to one side, the J value values life a lot higher. So these are not soft recommendations. When it comes to urban remediation, then the things that are being done are quite sensible. So the decontamination of 110,000 houses in Fukushima City, that was a good idea. It cost $370 million, but it's good value for money. The agricultural remediation, here again, and these even 20 years after the accident, then agricultural remediation, like adding ferrocin to cattle feed to reduce the uptake of radioactive cesium, which is the principal component that is the problem, replacement of contaminated soil, and then ploughing, liming, and so on, again looking to substitute to displace radioactive elements with similar elements, chemically similar and stable elements. They're a good idea. Food bans, we ourselves, how did we fare after Chernobyl? How did we do? We actually looked at these. Obviously, there were a number of things we could look at. There was a huge number of things we could look at, but we were restricted in the amount of time we had. But we did look at the UK response on land restrictions. The problem with that was that it took 26 years to lift the restrictions. And so banning lamb from certain pastures from entering the food chain, it took 26 years before they were removed. And by that stage, they were saving 8 seconds of life for the UK citizen, which is not very high, I think you will agree. An extreme consumer who eats loads of contaminated sheep meat, only contaminated sheep meat basically, and he'd lose 2.5 hours of life expectancy. So the sheep meat restriction should have been lifted earlier. I want to throw this one in to give some indication, because I've talked about loss of life expectancy, and I talked about it across a population, which is an average across a population. But what happens to those poor people who actually die as a result of the radiation that they get? They die as a result of a radiation cancer. What age do they die at? Well, the blue line shows their average age at death, and you can see from that they will tend to live into their 60s, and they have a 2-to-1 chance of living longer than about 50. So that's a further thing for you to think about. And then the loss of life expectancy for a radiation cancer victim is between 8 and 22 years, what that means is that on average, the radiation cancer victim will lose half or less than half the life expectancy he or she would lose in a fatal accident, such as a rail crash or a car crash. So there's a certain amount of gallows humor, perhaps you might think, in the last sentence there, but if you did have a choice, it's an unrealistic choice, but if you did have a choice, then radioactive fallout every time. Second method we looked at was to develop economically optimal strategies, modeling the deposition of fallout, its decay, and its contact with man in a fairly simple way to get a tractable model that could be used as far as optimal economic control is concerned. Modeling the evacuation process, that's the Chernobyl evacuation process, and the line, the dots on that graph, and then the line is the actual model, and then modeling the economics. For hundreds of potential accidents at nuclear reactors spread all over the world. And the method that was used was Richard Bellman's principle of optimality, which is basically the mathematics of you cannot do better than the best. Very often mathematics is concerned not so much with discovering new things, but is proving that what you knew all along was sensible. And in a sense, that's when Bellman talks, Bellman's principle is in a sense like that, but the mathematics to derive it, then spread it and apply it more to many problems can be rather complex, which is why we had Manchester mathematicians to do that for us. And a number of strategies were put together, and those illustrate the 5 possibilities under relocation, 3 possibilities under remediation, and then 3 possibilities under food bans. And so that's the spread, and that was the way in which these things were looked at. For most cases, for these hundreds of cases that were looked at, the optimal strategy was to carry out remediation early, not to ban foods, and to relocate on a partial basis, but then follow that up by full repopulation. And then for the remaining time, don't relocate at all. And permanent relocation, such as we've seen at Chernobyl, and such is de facto what's happening at Fukushima, that's only a good idea when you skew the cases to reduce or remove the cost of moving, which is a somewhat more unlikely case, but then and even in that case, it's only 2% of the cases. And then method 3 was the Open University, which used Public Health England's PACE COCO2 program suite. Looking at the spread of fallout from this reactor 45 miles from central London and 30 miles from central Southampton, and finding out the economic costs, and that includes the health costs for that. The idea was that a core melt accident occurred at a fictional pressurized water reactor on the South Downs of England, and the release was roughly of the same order as what happened at Fukushima Daiichi from a single reactor. So it's about a quarter of what actually emerged from Fukushima Daiichi. And when I say similar, this diagram, which I guess is a bit busy actually, but if we concentrate on the vertical lines there, the black dotted vertical line and the blue vertical line, it's looking at a number of radioactive isotopes. And if you divide the blue by 4, you more or less, in most cases, you get what was actually looked at very roughly on the South Downs reactor. For this, the The safe return dose was set at 10 millisieverts over the following year and applied 3 months into the accident. So if the dose was going to actually go was higher than 10 millisieverts over 12 months, was calculated to be, then you don't return. That's actually half the dose that the safe return dose that the Japanese authorities used. And again, to put that in context, if you actually receive a dose of 10 millisieverts per year for 50 years, that will reduce your life expectancy by 4.5 months. So there are 100,000 homes in the UK that face that as a matter of course as a result of radon seepage. So it is a pretty low dose. And remember that you wouldn't be getting a constant dose. The dose would be falling as the red line on the graph indicates there. But when that was put into it, this rather strict return criterion, even then, the expected number, that's the average number that you would expect from such an accident on the South Downs of England, 45 miles from central London, number of people needing relocation would be 620. I think you can see this is rather different from 335,000, and it's rather different from 160,000 people. So now we're starting to come to think about some conclusions from this. And mass relocation. It should not be the policy, the default policy as it has been in the past. The idea that you should do this, it's in every case, all of these things are saying, well, it's not impossible that you will want to relocate some people, but the number is likely to be small. And in many cases, don't relocate anyone at all. After a big nuclear accident where the core has melted and there has been a significant release of radioactive, very significant release of radioactive fallout into the atmosphere and the surrounding area. Remediation is sensible, and there are certainly things you can do to improve matters after a big nuclear accident. The way to judge those is to use the J value, and you can judge whether it is a sensible idea. And certainly as far as remediation is concerned, some measures which we judged even 20 years after the Chernobyl accident were coming out, as I mentioned before, as sensible. Yes, go ahead, do it. The total cost of an accident. Well, if the accident is managed in a sensible way, it's likely the cost of the accident is likely to be a few billion pounds plus the roughly similar cost of writing the nuclear reactor off as well. That's what the cost should be. So measured in single figure billion pounds. But if the example of Fukushima, the precedent possibly set by Fukushima Daiichi is followed, then the cost is going to rise by a factor of 100. And you're looking at 100 billion pounds, 200 billion pounds, 400 billion pounds, that sort of order. Now I'd like to address the follow-on question from that. So does it matter if we overspend by hundreds of billions of pounds? Maybe you think, well, surely it must have helped somebody. It must have helped at least the people. We've overspent, but we're helping the people who are living near the plant because they got this extra protection. No, it doesn't work out like that. There was positive harm done to these very people on whom this money is purported to have been spent. We know that because we have World Health Organization reports which tell us that. Even when people were compensated for losses, given free houses and a choice of resettlement location, the experience was traumatic and left many with no employment and a belief that they have no place in society. Tensions between new and old residents of resettlement villages also contributed to the ostracism felt by the newcomers. The demographic structure of the affected areas became skewed since many skilled, educated, and entrepreneurial workers, often younger, left the areas, leaving behind an older population with fewer of the skills needed for economic recovery. That's the first way, but that's not the only way. In a sense, that's the obvious way. The second way is the survivor's perception, and it's a logical perception that they are doomed. Suppose that the relocated people come to see the tens of billions or hundreds of billions of pounds that have been spent on them, not as a way of protecting them from harm, but as compensation for the damage that has been inflicted on them. They see themselves now as victims. Won't they now back calculate the extent of their harm from the vast expenditure that they observe? They may not understand the units of radioactivity and radioactive dose, but they certainly will understand when huge, vast sums of money are being spent. So why is the government? The government's never spent that amount of money on me before. Why is it doing it now? I must be in a truly bad way. That's the logic, and they see themselves as victims, almost certain to die young. Again, the World Health Organization. The designation of the affected population as victims rather than survivors has led them to perceive themselves as helpless, weak, and lacking control over their future. This, in turn, has led either to overcautious behavior and exaggerated health concerns, or to reckless conduct such as consumption of mushrooms, berries, and game from areas still designated as highly contaminated, overuse of alcohol and tobacco, and unprotected promiscuous sexual activity. I think a comment that needs to be made there is they now perceive themselves as destined to die young. And that's not a nice state for anyone to be in. I think the first conclusion from this, which has come out from this, is that relocation should not be the obvious policy of choice. We know that now, and even if we had no further information, we should be very hesitant about employing mass relocation after a big nuclear accident. We know what happened at Chernobyl, and we know what happened at Fukushima Daiichi. In both cases, the relocation option was exaggerated. In the case of Fukushima, exaggerated completely. But we'd like more information to guide the decision makers early on. And this is indeed possible. So looking to the future, if we look towards real-time mapping of the fallout using a mixture of fixed and mobile measurement systems, and here work at Bristol has shown that unmanned drones are now highly possible in order to give mobile measurements. We can feed that into a model, and we could no doubt improve the models that give the dose profile over time, not only from the ground shine from the radiation, but also from the food ingestion, and we can develop those and use those. And then we can apply the J value continuously as the accident develops, given we've got one of these very unpleasant big nuclear accidents actually happening, but we can now supply the decision maker with information so that the Japanese Prime Minister does not have to consider evacuating Tokyo. These images are courtesy of Professor Tom Scott of this university. And the upper left-hand photograph there, or imposed photograph there, shows a radiation map of contamination around a disused uranium mine in Cornwall. And then underneath it, you can see the flight path of the drone, which obviously is shown on the right-hand side, this radiation mapping zone. So we can do that, and we can do that in real time. So the big lesson from the NREF study is how small the radiation damage has been to the members of the public from even the biggest nuclear meltdown accidents. We've got most of the harm coming from the unjustified fear and worry, and from the social disruption and dislocation, which is an inevitable concomitant of evacuating on a permanent basis, relocating hundreds of thousands of people. It's become the solution, the so-called solution has become the problem. Remediation is a good idea, should become the watchword. We can and should cope effectively with a big nuclear accident in the future, much better than we have done in the past. And if we do that, we save ourselves hundreds of billions of pounds, but we protect the people better. Thank you.